All right. So, good morning, everyone. Today's Wednesday, and my primary plan for the day is going to be starting Chapter 12. Up until now, we've been talking about a lot of different varied thermodynamics concepts, and now we're going to focus specifically on the laws of thermodynamics that sort of are at the center of all of that. Whoops. First, though, I would like to reiterate that you, at this particular point, should be done with the Chapter 10 and Chapter 11 homework and quiz. If you're not, then I do recommend to be working on them, especially as we'll be spending about a week on Chapter 12, and then we're going to move into the area of taking our first test. So I expect a couple days into next week, learning Chapter 12. We'll take a day of study to so that you can work on the homework. We'll probably spend a day reviewing for the test, and then I'll probably make the test available to you towards the end of either the end of next week or the start of the week after that. We'll talk details soon. But this is just a reminder, be working on the assignments, especially as study material for the test as we approach test 1. Let me know if you have any questions or issues thus far at this particular time before I dive into Chapter 12. Additional reminder, no lab this week. We're doing every other week, so our next set of labs will be next week. I'll make sure to have a full schedule laid out for the coming weeks as this weekend. By the start of next week, I'll have a full schedule for what the next couple weeks will look like. So, if there's no questions at this particular time, let's get started with Chapter 12. We're now going to be focusing on the laws of thermodynamics directly, and kind of similar to Newton's 3 laws of motion. The laws of thermodynamics are very important statements that all scientists, not just physicists, use to help us understand the universe around us, help give us a framework for which energy itself operates. They're called the laws of thermodynamics, but they kind of describe energy in general, not just thermal energy. And there's famously 3 of them. At least historically, there's 3 of them. There's technically 4, though, but it was kind of added after the fact. So the current statements on screen are the laws of thermodynamics. We'll look at each one individually in turn. And there are numbered 3 of them: first law, second law, third law, and these were the 3 created first, as a set of 3 that most people are familiar with. After the 3 were made, some scientists decided that we needed an extra one, but since everyone was kind of already used to the 3 laws of thermodynamics, kind of like how Newton's laws of motion come in a set of 3, they didn't want to make a 4th one. So instead, they added the 0th law of thermodynamics, kind of as a prologue statement. It's not really new information, but it's kind of like a primer that physicists at the time felt needed to be kept in mind before reading the rest of them. It's a very weird situation. We're going to talk about all of them. I don't really care for this way in which they're numbered or the way that they were made like this, but this is what they are currently called in academic textbooks, kind of frustratingly. So, the 4 laws of thermodynamics. I'll go from 0 to 3. The 0th law of thermodynamics reads that if objects A and B are in thermal equilibrium with a third object C, then objects A and B are in thermal equilibrium with each other. The first law of thermodynamics, which is the one that most people have heard of, is also known as the law of conservation of energy. Energy cannot be created nor destroyed. The total energy level of the entire universe is a fixed constant. Energy can be converted from one form to another or transferred from a system to the surroundings or vice versa. So, can't be destroyed, it's just transformed and shuffled around. We've been using this statement a lot, actually. So, even as far back as Physics 1500, and you've probably used it before then, too. So, of the four, this is probably the one you're used to hearing the most. Second law says the entropy of the universe does not change for reversible processes and increases for spontaneous processes. In other words, no system for converting energy between various forms can operate at 100% efficiency. We'll talk more the specifics about that one in a couple of days. And the third law of thermodynamics states that the entropy of a system approaches a constant value as its temperature approaches absolute zero. Again, we'll talk about that one more in depth along with the second one. For right now, these are the three laws. Sorry, these are the four laws. And we'll expand on each one over the next week. Look at what sort of math, what sort of concepts each one can help us with as we go along. Well, okay, yes. Before looking at each law in detail, it's important to keep a few vocab terms in mind. First is the idea of a thermal system. I think my recording software is currently glitching out. My apologies. Make sure I didn't lose signal while that's going on. Okay. Technical issue over. Apologies. So. Excuse me. Oh, jeez. Very sorry. Okay, so some vocab words. Thermodynamically speaking, when we refer to a system in these coming notes, that's going to refer to the portion of the universe that you're specifically examining in a specific context. So if, say, you were working on a sample problem that involved, one campfire roasting one marshmallow, those are the objects you are studying. You are looking at the interconnectedness of those particular objects and how energy from one affects the other. Those objects are your system. They're just the things that you're looking at. The surroundings is everything besides your system. Everything else in the universe that isn't the two objects you're looking at, but still technically exist. They exist in the sense that energy could hypothetically travel from your system, from the objects you're looking at, out into the surroundings. Say again, if your system is one campfire and one marshmallow, well, there's going to be thermal energy from the fire that doesn't end up in the marshmallow, because the heat from the fire is going to rise. Not all of it's going to end up in the marshmallow. A lot of hot air and ash is going to keep rising up into the air regardless. And so, energy from the system is able to leak into the surroundings, and vice versa. But these words will come up from time to time, so just wanted to get the context in which they're used settled for the time being. So, the first law in the order is actually the 0th law, and this one won't take very long to go over because it's easily the most straightforward out of all of them. It's just the transitive property of temperature, really. In math, the transitive property says that if A equals B and B equals C, then therefore A must equal C. And 0th law just says the same thing about temperature. If, object A is the same temperature as object B, and if object B is the same temperature as object C, then object A and object C must be the same temperature as each other. Doesn't necessarily mean that they have the same thermal energy level, just means that their temperature is the same, so their particles have the same average energy level. I'm really not quite certain why physicists of the last couple centuries decided that this law was important enough to tack on to the other three. But it's here, and it's worth, I guess, noting for the historical value and for the fact that it's kind of funny that we have 4 laws of thermodynamics even though we only really care about the 3. So that's the 0th law. It's not really that important, but it's on the chart. So let's instead begin focusing on the first law of thermodynamics, which we've already kind of been using throughout this class and throughout Physics 1500. The idea that energy can't be created or destroyed, it has to come from, if you bring energy in, it has to specifically come from somewhere, and if you get rid of energy, then it has to go somewhere in the exact same quantity. We've used this several times already in, say, within this particular class, the formula Q gained equals negative Q lost. The idea that if one object gains energy, another object had to lose the same amount of energy. And in Physics 1500, we would use this as we transferred between different energy types, like how if you hold an object in the air and then let it fall, that would allow the GPE in the object to transform directly into KE. So the law of conservation of energy should be one that you're pretty familiar with. But we're now going to begin using it mathematically in a slightly different context. Say, for example, you have a machine, some machine, and let's just use your car engine for an example. The way that your car engine works is you put gas into the car, and in doing so, you are adding energy into the system in a potential form. That energy is going to get used up, the gas will be burned, it'll explode, it'll make combustion happen inside the engine, and as that energy is released, some of it will be used to do work. But in all likelihood, not all of it will be used to do work. We've talked a lot about how friction kind of ruins things a lot on planet Earth. Friction tends to reduce energy levels where you don't usually want them reduced. In the case of a car engine, for an example, the friction within the parts of the machine cause some of the energy that is being exchanged within the engine to not be turned into work in the wheel wells. Instead, friction, like say between the piston and the piece of metal housing the piston, friction between those two parts would slow the piston down, and as a result, some of the energy that could have become work is now going to become thermal energy inside of the engine block, because friction just turns mechanical energy into thermal energy, as you can demonstrate by rubbing your hands together and letting friction turn the kinetic energy of your hands into thermal energy in your hands. As a result of this, when you give energy to a machine to let it do work, very often, not all of the energy you put in becomes work output. And in turn, sometimes it's possible to say, put a certain amount of energy into something and it do more work than that energy you put in, but that would take up additional energy that the system already had in the first place. I'm hand-waving a little bit. Let's actually look at the formula that's currently on screen. Delta U equals Q plus or minus W. This is a formula for calculating the change in the total internal energy level of a specific object. The delta U term represents the energy in total, the lump sum of energy that an object may have, or that a machine may have. In order to change a system's energy level, you have to either give it extra energy or you have to take energy away from it. And that is what the Q and the W represent. So Q represents when you add heat to a system. So say, for example, you have that car engine and you introduce thermal energy into it to try to get it to do work. You're adding energy into that system. That would be the Q. You're adding energy to it. Hypothetically, you could also remove thermal energy from it, in which case Q would be a negative number. So Q represents the increase or decrease of an object or machine's thermal energy level as a process goes on. So adding or taking away thermal energy is one way to change an object's energy level. The other primary way to change an object's energy level is for it to use up some of the energy that it already had by doing work. When you do work, you use up the energy that you have stored up in order to perform various actions. So the second term here, the W, represents the work that the machine is doing. If the machine does 10 joules worth of work, then it has 10 joules less energy than it would have before it performed that task. So, for this particular formula, to change an object's energy level, you must keep in mind how its thermal energy level changes and how much work it is doing. There is one thing to note about the W in this formula. I put a plus or minus sign in front of it because which sign you use depends on whether the machine is doing work or if the machine is being worked on. I'm going to start using a slightly different example here, and I'm actually going to tab ahead a few slides, really just to show you a certain picture. So, we'll get to this formula. We'll get to this formula. For right now, what I really want to show you is this image currently in the bottom left-hand corner. This is a pneumatic piston. It's a system where you have basically an amount of gas inside of a canister, and that gas is able to expand or contract as you heat it up or cool it down. And as it expands, the gas inside the canister wants to take up more space, so it's going to exert more force on the inside of the canister. And as it does so, there is a piston attached to the canister as one of its sides that if the gas expands, it pushes out on the piston, allowing it to expand, but also physically pushing the piston outwards. You can kind of see that in this picture here. If this smaller version of the canister is its original size, if you heat up the gas, it'll push on the piston inside the cylinder that's able to move. That will drive the piston outwards so the gas can take up more space. This is one of the earliest examples of a type of machine that humans would use in order to do work for us. I'm going to specifically describe it in terms of a train. Old steam locomotives. If you've ever seen a steam train in motion, either in person or maybe in an old movie, then the way that they work is you boil water inside of the train engine, and that vapor is technically a gas, that steam is a gas, that steam gets funneled through various parts of the device into pistons that will extend as the gas is introduced and expanded to push forwards on the wheels, and then it systematically pulls the gas back out of the piston to contract it and pull that caster backwards. And so that repeated in and out motion of the piston causes the wheels of the train to spin. And that's how old steam trains would work. So we use pistons, pneumatic cylinders, to extend when heat is introduced into them, and in extending, that object is able to do work. It exerts force as it extends out some distance. Force times change in distance is work. So piston does work as it extends and contracts back in when you take thermal energy back out of it. It's one of the earliest examples of a machine that humans would use to do work for us. And it's an example we're going to come back to a lot as we're talking about, well, how thermal energy can do work for us in this particular chapter. It's going to be a very common example for the next week or so. So this is called a pneumatic cylinder, just so that when I say that term, you are aware of what I'm referring to. It's very similar to a hydraulic system. Hydraulics just use liquid, whereas pneumatics use gas. So if you've heard of hydraulics in a car, it's a very similar process. It's just it's liquid inside of a cylinder that is expanding, contracting, being moved around, whereas a pneumatic system is gases expanding and contracting and moving around. So this is the example I want you to keep in mind as we are looking at the next couple examples. This is the image I want you to keep in mind. Let me know if there's any questions or issues or inquiries thus far. You're also allowed to type them in the sidebar, and I will see them as they come up. Hold on. Has there been a weird wind? Give me just one sec. I feel I've discovered a technical hiccup I didn't know existed. Okay. So, that's a pneumatic cylinder, and I'm going to be referring to that type of device as I continue to describe this particular equation here. So the way that device works is you have gas in the cylinder, you introduce thermal energy into it, that's going to increase the gas's temperature, that gas is going to try to expand. As it expands, the piston is able to push outwards and do work. So you introduce thermal energy into the piston, and then the piston does work on your behalf. So the thermal energy introduced is the Q term, and the work that the machine does is the W term. So if the piston is doing work, if it's pushing outwards, exerting a force on some object as it moves some distance, then that W term would need to be a negative number. Because from the piston's perspective, plugging in a positive Q represents that the piston is gaining thermal energy. You're putting heat into the gas of the piston. So for this particular formula, positive numbers represent energy gain. But if the piston is doing work, the act of doing work inherently means that you are using up energy and sending it somewhere else. So as the piston expands and as the metal piston end pushes on something, like it pushes forwards on the wheels of the train, whoops, thank you for letting me know. Yes, I think I closed the PowerPoint, and thank you for letting me know. My mistake, I apologize. It should be back now. Yes. Okay. Thank you for letting me know. So, we're back on delta U equals Q plus minus W. Positive numbers in this formula mean energy gain on behalf of the piston. Negative numbers mean energy loss. So if the piston is doing work, it's pushing outwards on the wheels of the train, it's giving energy to those wheels. It's taking up energy that it had inside of it and putting them into the wheels of the train in order to make them spin. And so by doing work, that reduces the total energy level of the entire machine. So if the machine is doing work, then the work number you plug in would need to be negative. Conversely, it is possible to do work on a piston like this because, say you've introduced thermal energy and the gas has expanded, the piston arm has been extended. It's possible for some other person or machine to push inwards on the piston and put energy into it. You do work pushing the piston end inwards, and that would force the system to contract. That would force the gas inside to contract back down to a smaller volume. That would be doing work on the system because you are literally pushing into and on the system. You are giving energy to it as you use up the energy in your arm to do that action. In that sense, doing work on the piston gives it energy back. And so the reason the plus minus is in this formula is because work will very specifically be, the value you plug in will be plus or minus based on whether the piston is doing the work and giving up energy or whether or not the piston is being worked on and is gaining energy. So the Q might be positive or negative depending on the direction of heat flow, whether it's gaining or losing heat. The W will be positive or negative depending on whether the piston is doing work or whether something is doing work on the piston. And those two factors combined will determine if delta U, the total energy, the change in total energy level of the system, will either increase or possibly decrease. I've been hand waving a lot. Let's actually put a couple of numbers to this. Next slide summarizes these ideas. All right. So let's look at a quick example to try to put some numbers to all of the things that I have been saying. We're going to look at one of those pistons, one of those pneumatic cylinders that I've been talking about. And the particular pneumatic cylinder we're looking at has a piston, and we are going to add 1,000 joules of thermal energy to it. So let's say you're a steam train operator. You've got the steam engine boiling, and that burning steam engine is going to add thermal energy to the gas inside of the piston that drives the train's wheels. So we've added 1,000 joules of energy to that system. The gas inside the piston will expand, and as it expands, it's able to push outwards on the actual piston part, and that piston is going to extend outwards a distance of 2 meters, and while it is extending, it will exert a force of 400 newtons. So as it pushes outwards, it is going to extend. That is a force exerted over a distance. So my first question is, how much work would this piston be doing? And to answer that, I want to dig up an old formula. This is something that should look familiar from Physics 1500. Work equals force times displacement. In order to do work, you exert force on something as you move it some distance. For example, if you wanted to pick something up, you would have to exert a force on it upwards as it moved some distance upwards. And in doing that work, you use up energy in your arm and you give it to the calculator. I'm using my calculator. You use up energy in your arm, you give it to the object you're lifting. Now it has the energy that you gave it. Excuse me. So, this is the same work formula, the same definition of work from Physics 1500. The machine is exerting force as it moves some distance. So it exerts a 400 Newton force as it extends a distance of 2 meters. So that tells us that this particular machine is doing 800 joules of work. So that's the work that this particular device is accomplishing. That's pretty good. Now, the next question is, what is the change in the piston's internal energy level as a result of this entire process? We gave it 1,000 joules of thermal energy. It then proceeded to do 800 joules of work using that energy. So we gave it more than it ended up using. So we can use the first law formula here, delta U equals Q plus minus W, to try to figure out, well, to prove mathematically how much energy was left behind inside of the piston, the gas in the piston. So delta U is what we're solving for. We want to know how much energy has been left behind inside of the piston. We gave it 1,000 joules of energy. It proceeded to use 800 of them. So the system did 800 joules of work. That means that it gave 800 of those joules away to something else. That means that there's 200 joules that was left behind inside of the system. I guess you could consider the goal of the machine to just be an energy bypass system. You want energy to go from the source into the object that's being worked on, and so you kind of use the piston as an intermediary. You put energy into the piston uses the energy to do work and give the energy to the next object. But it's not able to do so with 100% efficiency. Some of that energy was left behind. And this happens in pretty much every machine ever. All machines, if you give them some amount of energy, aren't able to use all of it. Some of it always ends up left behind as thermal energy trapped inside of the machinery. This is true in cars, where there's literally explosions going on inside of the engine, and, cylinders are moving, pistons are moving inside of their cylinders. There's friction in there. That takes up some of the energy that would have been used for work, but couldn't because friction took it away. So in the case of a car, if you say put in 1,000 joules of gas, you might only get 800 joules of work done out of that gas, and 200 joules would just be left behind, trapped as thermal energy inside of the engine block, just making it hot. It's not accomplishing anything, it's just making the system warmer than it otherwise would have been. All machines do this, and that's why all machines have the capacity to overheat. It's why your computer might eventually melt itself. It's why your phone heats up if you use it a lot and don't dim the screen. It's one reason why the human body can get overworked and overheated, because mechanically speaking, your muscles work like a machine. There's an energy exchange as you do work, and there's friction inside your muscles as muscle fibers move across one another. And so the friction in your own muscles causes your own body temperature to heat up as you exert yourself. And that's why you get really warm and tired when you go for a run or exist in a summer day. All machines do this. All machines, for the most part, all machines are inefficient, and some of the energy you give them is going to be left behind as heat inside of them. Now, this particular formula, it is possible to get a negative answer for delta U. And that would be if, say, it was being cooled and you were taking a bunch of thermal energy out of the machine using a separate system. So it is possible to get a negative answer here. But I want to just put in your head the generality that all machines are inefficient, and when they do work, some of the energy that they had won't end up as work output. Let me know how this sounds and feels thus far. This... I know that when I teach Physics 1500, I tend to at least touch on this particular topic, especially as friction comes up, because friction is the primary reason this happens. But if it does sound completely new to you and you need me to go back over something, let me know. I do have one more example related to this that I want to discuss briefly. Oh, that's a different example entirely. I lost my train of thought for a second there, sorry. Forgive me. In my memory, my notes were in a slightly different order, and I lost track of myself for a second there. I apologize. Give me just a sec to look over some things. Whoops. Okay. Yes, I'm going to talk about this in a slightly different order. So if you have the notes up that are currently saved to Brightspace, which are the notes that I'm following along with here, I'm skipping around a little bit because the order that they are in the slideshow is not the way in which my brain was remembering them or was wanting to talk about them. So sorry for that little hiccup there. Let me look quickly back at... I'm jumping around all over the place, sorry. All right, so let's look back at this example we just did real quick. We've determined that if we give this cylinder 1,000 joules of energy, it's capable of doing 800 joules of work. So that leaves 200 joules behind inside of the system. With that information, it's possible to determine the efficiency of this particular machine. All machines, and that does include the human body, so everything that moves has some efficiency rating, because everything that moves needs some amount of energy in order to make it move, but not all of the energy that it has is necessarily going to end up as work, is going to end up in the form of kinetic energy, like what we just saw with that last piston question. For that particular piston, we have the knowledge that if we give it 1,000 joules of energy, it can do 800 joules of work, and that leaves 200 joules behind, making the piston hotter. And if that process continues, the piston will eventually overheat. We can use that information to determine the efficiency of this particular machine. There's a formula currently here, circling it on the top left-hand side of the screen. It's the formula for thermal efficiency, and in brief, something's efficiency rating, it's a percentage that demonstrates how much work something can do with the energy that it's given. For example, if a machine was 100% efficient, if you gave it 100 joules of energy, it could do 100 joules of work from that energy. Just perfect one-to-one ratio. The formula says that in order to calculate the efficiency, and the efficiency variable is this nth value right here. So nth is the efficiency number. You divide the machine's output, the result of the machine's work, by the machine's input, by the amount of fuel that you gave it to perform that task. So, in the context of the example we just looked at, the machine's input was 1,000 joules of energy. We gave it 1,000 joules of heat in order to perform a task. It did 800 joules of work from that energy. So our output was 800, our input was 1,000. That would make our efficiency rating 0.8. 0.8 out of 1. That correlates to an 80% efficiency rating. This piston that we described earlier is 80% efficient at taking the energy it's given and doing work from it. All machines have an efficiency rating like this, and that does actually include the human body. I think, and I'm not a biologist, so this is not my area of expertise, this is just a statistic that I've been told, is that the human body is, mechanically speaking, about 20% efficient. So the way that you fuel your own body is you eat food. Say you eat 100 joules worth of food, and the body is able to take 20% of that incoming energy and make it available for you to use in your muscles to do work. So if you eat 100 joules worth of food, 20 joules of that is what you'll be able to actually use in your muscles. So 20% of the food you eat is actually usable muscle energy for moving around and accomplishing tasks. The remaining 80% goes somewhere else in your body. A lot of it just goes into making thermal energy to keep you warm, because we are warm-blooded mammals. Some of it goes into your brain functioning or your organs doing their jobs. Some of it is lost to the friction inside of your muscles. So, mechanically speaking, just in terms of food to work output, humans are 20% efficient. The piston that we were looking at a second ago in that sample question is about 80% efficient. And on average, you don't see very high efficiency scores for most human-made machines. In fact, the human body being 20% is kind of higher than most efficiencies you'd naturally encounter in the world. The piston being 80% efficient is actually basically unheard of. That would be one of the most efficient machines in the world if an actual piston was able to operate based on those numbers. In real life, efficiency scores tend to be really, really low. Friction tends to take a lot of energy away, slow things down. And again, that's why all machines eventually overheat, is they're inefficient, and most of their energy doesn't end up as work output. It ends up as thermal energy, just making them hotter. And so these are the formulas that we use to describe those facts. Let me know any and all questions or issues or things you'd like me to go back over real quick. I'm going to take just a second. Okay. Whoops. I've been going on for a while, and I think that's probably a pretty logical stopping point for today. We've talked about as much as the first and the zeroth and first law as I think are really needed at this particular moment. So, any questions at all, chime in, let me know. You can type them out if you want to. And what I will do is be here for you to hop back in if you have any questions over the next hour or so. I'll be working on getting some more examples of first law that we can look at tomorrow morning. So that is all the stuff that I wanted to make sure to cover today. If there's no questions right now, we'll take a break. I'll be here for the next hour for you to jump back in if you have questions or needs as you ponder this or work on your homework. Do make sure to be working on and to try to finish up the chapter 10 and 11 stuff so that as we near the test, you can look back over it. Don't let it sit for too long without doing it. And yeah, we'll pause here and jump back in with if you have questions. And if I don't see you again today, I will see you tomorrow.